Welcome back to Statistics. I'm Dr. Jeff Groh. Today we're going to talk about sampling distributions. And estimates. Suppose you have some population distribution. Maybe it's heights of individuals. There are more people with a particular mean height than there are people who are very tall and people who are very short. Now, this is the population distribution for these heights. Suppose you have a sample then and you find the mean of the sample, x bar. The mean of the sample might be less or more. It won't necessarily be exactly the population mean. And each time you take another sample of the same size, you might get a different mean. There will be a bunch of different means depending upon the different samples that are possible. For instance, if you take a look at, say, 32 students in a classroom, those 32 students would constitute the population. If you randomly select 5 individuals from the class and measure their heights, then you'll have a sample mean from the sample of 5 students. But there are many ways of choosing 5 students from the class. There is a distribution then of sample means. How does the distribution of sample means compare to the population distribution? For means, if the population is normally distributed, then the distribution of sample means will also be normally distributed, but usually have a smaller standard deviation. And so it'll be more bunched up towards the middle. So this is the population distribution, and this is the distribution of sample means. Also normally distributed, but narrower, and so it'll have a peak that's higher towards the center. Proportions taken from a population are also distributed normally. So you'll have a distribution of sample proportions from a population. Say, for instance, you're estimating the opinion of a population who may favor or disfavor a particular proposition on a ballot. There are many different sample proportions that you'll get. Let's suppose you sample 10 people, and 6 of the 10 are in favor of the proposition on the ballot. But then you sample another 10 people, and 4 of the 10 are in favor of the proposition on the ballot. So you had 6/10 and also 4/10 as sample proportions. You'll have a distribution of these proportions. If the population has a normal distribution, the distribution of sample proportions will be normal. That's not necessarily true for variances. Recall that's sigma squared. They can't be negative, so the distribution will be skewed right. The sampling distribution of a statistic, like the mean, is the distribution of that statistic over all samples of a fixed size. Let me give you a very simple example. Suppose the population is heads and tails, and sample 1 is heads, and sample 2 is tails. Let's assign a random variable value of 1 for heads and 0 for tails. The population mean will be 1 plus 0 divided by 2, or 1/2. Here we have a mean of 1, and on the second sample we have a mean of 0. The mean of the sample means will also be 1/2, which is the population mean. And in general, that's going to be true. The mean of the sample means will be the population mean. This is, by the way, what makes sample means an unbiased estimator of population means. We'll talk about that more in a minute, but first let me point out something. First, the mean of the sample means is the population mean in general, and second, and very importantly, the distribution of sample means tends to the normal distribution as n goes to infinity, which means that the normal distribution is of fundamental importance, regardless of what the population distribution is. As n tends to infinity, the distribution of sample means will tend to the normal distribution. By the way, the mean of the sample variances will also be the population variance. However, the distribution of sample variances is skewed right. It will not tend to a normal distribution. Another important statistics for us is the sample proportion. If P is the population proportion, and P hat is the sample proportion, then the mean of the sample proportions will equal the population proportion. Also, the distribution of proportions will tend to a normal distribution. Of course, as n goes to infinity. A statistic used to estimate a population parameter is called, oddly enough, an estimator. A statistic is called an unbiased estimator if its expected value is the value of the parameter. In particular, the sample mean, the sample variance, and the sample proportion are unbiased. Estimators of their respective parameters. On the other hand, the standard deviation is biased. Variance is unbiased. Standard deviation is biased. Another example of a biased estimator is the median and the range. There's something important called the central limit theorem. In a population with a mean, mu, and variance, sigma squared, regardless of its distribution, the distribution of sample means, x bar, tends to the normal distribution. As n goes to infinity. And by the way, if the population starts out as normal, then the distribution of sample means will be normal. As a rule of thumb, if the samples have size n greater than 30, then the distribution of sample means will be close to normal, with the mean of the sample means being the population mean, and the standard deviation of the sample means will be the population standard deviation divided by the square root of the sample size. You can see how the bigger n is, if n is say 100, then the standard deviation of the sample means will be just 1/10 of the population standard deviation. So you get a narrower distribution for the sample means. We should also point out if the population distribution is normal, then the distribution of sample means is normal for all n, even smaller n besides those bigger than 30. The central limit theorem and our rule of thumb allow us to apply the normal distribution to calculate probabilities, even in situations where we don't know the population distribution. Here's an example. A soft drink vending machine is set to dispense with a mean of 200 milliliters. So this is mu, and a standard deviation of 15 milliliters. What is the probability that the mean amount dispensed on a random sample of n equals 36 is at least 204 milliliters. So what's the probability that x is bigger than or equal to 204 milliliters on a sample of size 36, given that the population mean is 200 milliliters with a standard deviation of 15 milliliters? Since the sample size is bigger than 30, we can assume that the distribution of sample means is normal. The distribution of sample means will satisfy the mean of the sample means will be the population mean, which is 200 milliliters. But the standard deviation of the sample means will be the population standard deviation divided by the square root of the sample size. The population standard deviation was 15 milliliters, and n is 36. So we end up with 15 divided by 6. On my calculator, I can use normal CDF. The lower endpoint is going to be 204. For the upper, we can choose anything at least 6 standard deviations greater than the mean. The mean is 200. We need at least 6 of those, so anything greater than 215 should work. Let's just use 300. The mean that we will use is 200, and the standard deviation that we use will be 15 divided by 6. And the probability that we get is 0.055, about 5.5%. So having a sample mean that is greater than 204 is different from having just a single cup having a size bigger than 204. If you're trying to find the probability that a single cup has more than 204 milliliters, you'll have to use the standard deviation of 15 if you know that the population distribution is normal. If you don't know what the population distribution is, then we can't use this method at all. However, for the samples of size 36, since that's bigger than 30, those sample means will have a distribution that is very close to normal. And so we can use these normal probabilities to calculate the probability that the sample mean is bigger than 204 milliliters. For another example, "18-year-old male heights are normally distributed with a mean of 68 inches and a standard deviation of 3 inches. First, find the probability that an individual selected will have a height between 67 and 69 inches. So one individual selected at random. And second, find the probability that the sample mean is between 67 and 69 inches when the sample has size n, 9. Suppose we select 9 individuals and find their average height. What's the probability that the average height of those 9 individuals is between 67 and 69? In solving number 1, we will, of course, use normal CDF. The lower bound will be 67. The upper bound will be 69. The mean will be 68. And the standard deviation will be 3. If we plug all of that into our calculators, we get 0.2611, about 26% chance of a single individual having a height between 67 and 69 inches. Now, what is the effect of having a sample of size n? We can use the normal distribution because, despite this being small, the population is normally distributed. And so for part 2, you also use normal CDF with lower of 67, upper of 69, mean of 68, but the standard deviation that you'll use is different. It's going to be the population standard deviation divided by the square root of the sample size. Notice that the square root of 9 is 3, and any number divided by itself is 1. So you can either type in 3 divided by the square root of 9, or you can just type in 1. Now the probability that you get, since the standard deviation for the sample means is slightly smaller, you get a larger probability. You get 0.683 if you round it, about a 68% chance that the sample mean will lie between 67 inches and 69 inches. As another example, let X be white blood cell count per, say, milliliter. We will assume that X is normally distributed with a mean of 7,500 and a standard deviation of 1750. Result lower than 3,500 is an indicator for leukopenia. First, we'll find the probability that X is less than 3,500 for any given individual test. If a doctor orders 2 tests 2 weeks apart, find the probability that the mean is less than 3,500 for the 2 tests. If the doctor orders a 3rd test, what is the probability that the mean of those 3 will be less than 3,500? I'll write the mean for the population here and the standard deviation here. In solving problem 1, we will of course use normal CDF. We are assuming that the population is normal. The lower needs to be at least 6 standard deviations below the mean. Let's just use a lower of 10,000 just to be super safe. The upper is going to be 3,500, the mean, 7,500, and the standard deviation, 1750. We'll type that into our calculator. Normal CDF, lower, negative 10,000, upper 3,500, standard deviation of 1750. I'm getting 0.011. Less than 1% chance that a single individual test will be less than 3,500. This is unusual. On problem 2, we also use normal CDF. The lower, let's do the same lower and the same upper. The mean will be the population mean, but the standard deviation is going to be 1750 divided by the square root of 2, since we're using 2 samples this time, 2 tests. So normal CDF. The only thing that changes is the 1750 divided by the square root of 2. In this case, the probability that I'm getting is expressed by my calculator as 6.14 times 10 to the negative 4. Moving the decimal place 4 units to the left, we're getting a probability that is very small indeed. This is highly unusual to get 2, having a mean less than 3,500. So, with the first test, there was still a 1% chance that we were normal, but that the test was just a fluke. 1% probability, even if our mean is 7,500 with a standard deviation of 1,750, of getting a single test lower than 3,500. A 1% chance of us still being normal and not having the condition of leukopenia. However, once we've done the test twice, now the probability that we're still okay is quite small, much, much smaller than 1%. On part 3, the only thing that changes is we divide by the square root of 3 this time. So going back to our normal CDF, the only thing we change is the 1750 divided by the square root of 3. Now the probability that it's giving me is 3.77 times 10 to the negative 5. Moving that decimal place 5 points to the left. Gives us a probability that is very tiny indeed. So we can be quite sure now that the result is indicating leukopenia and not just some random fluke of the test. We give an introduction to hypothesis testing. Based upon the following principle, if the probability under a certain assumption or hypothesis is small, and by small we mean less than 5%, less than 0.05, we conclude that the assumption or hypothesis is probably incorrect. In the last example, we calculated certain normal probabilities and found that under certain conditions the probabilities were quite small. Those probabilities were based upon the assumption that the mean really was 7,500 with a standard deviation of the population of 1,750. If we took the samples and had values that were smaller, had a smaller mean than 3,500, the probability that the population mean really is 7,500 is quite small. It must be that for that particular patient, the population mean really isn't 7,500. It must be smaller than that. As an example, for a soda bottler, we hope the mean for a 12-ounce can is 12 ounces. The standard deviation is going to be about 11/100ths of an ounce, let's say. For a sample of size n equals 36, that's bigger than 30, that's a large sample, so the distribution of the sample means will be normal, or at least may be assumed to be close enough to normal that we can use the normal distribution to calculate probabilities. We find the sample mean to be 12.19 ounces. What I want to do is find the probability that the sample mean is greater than or equal to 12.19 ounces for sample sizes of size 36. We will, of course, use normal CDF. The lower will be 12.19. The upper needs to be pretty big. Let's assume 50 for sake of argument. That's going to be way more than enough. The mean should be 12. The standard deviation that we will use here is not going to be 0.11. It will be 0.11 divided by the square root of 36. So, crunching that into our calculators, the lower, 12.19, the upper, we'll just say 50, mean of 12, standard deviation of 0.11 divided by the square root of 36. And I'm getting a probability that says 1.85 times 10 to the negative 25, which, for all practical purposes, moving the decimal point 25 places this way, you'll have 0 point and then 24 zeros followed by a 185. This is 0.000 and a whole bunch of other zeros before you finally get something non-zero. As far as we are concerned, this is a very improbable event. Since the sample mean was 12.19, which is bigger than 12, on this sample size of 30, we conclude that the machine actually produces an average that's bigger than 12 ounces. It follows that the machine needs adjustment. I hope you've been careful to this point. N is the population size. And little n is the sample size. The way in which we write things, the case is often important. Uppercase versus lowercase will have different meanings or connotations. So please, use the correct case. When using this estimate here, we are assuming that the population is infinite. If the population is not infinite, and the sample size becomes a significant proportion of the population, there is a slightly different value to use. If 1 the population is finite, 2 sampling with replacement, and 3 the sample size is at least 5% of the population size. then it follows that the standard deviation of the sample means will be the population standard deviation over the square root of n times the square root of another factor, the population size minus the sample size over the population size minus 1, all under a radical.